So I'm going to talk about where we are today and where we're going with robotics. I mean, most of us are familiar with industrial robots. Well, these robots are now escaping their cages in the manufacturing plant and moving towards the human. And we are creating an amazing new synergy between robots and humans. Let me just illustrate this with what our students are doing in class. So what we can see here, is a robot fighting with a student. So you need to perceive, to see, you need to react, and to react you need to plan. This is a little bit of an illustration of where robotics is today. We are combining the perception, the planning, the action, the design of a mechanism that is allowing us now to see applications in real time, bringing those kind of interactivities. We are seeing doctors operating in many different surgeries through robotic devices and through haptic interaction. So the small incision, the surgeon is going to operate from outside. The patient recover in very quickly in few days. And this is happening over and over every day. Many operations are pursued in all around the world. We are using catheters as well, and these catheters are directed and controlled by haptic devices, a robotic sort of systems. We just saw the impact in social interaction between robots and human. We are seeing a lot of development in the services, bringing robotics to many different fields of applications. We are seeing human augmentation with mechanisms, exoskeletal systems that are allowing us now to increase the muscle power of a human so you can carry heavy loads without feeling the weight. We are not even started. There are so many things that are coming to the world of robotics, and I'm going to take an example, illustrate all the problems that robotics can address. And this is one example of them, archaeology. Archaeology underwater is a very challenging problem because divers can go to 30 meters, 40 meters. This is a boat off the coast of France, very close to Toulon. This boat from the 17th century, the boat sunk, and now it is at 100 meters. We cannot reach it with divers, so we sent robot, but the robot can see, so we decided we needed really to operate on that side. So the only way we can do it is by using a suit, and the human is going to go inside the suit, and the operation is very, very complex because now we have to operate the suit from outside, and the human is going to use the hands to be able to catch and bring those objects underwater. A lot of things are there, and many boats all around the world. What can we do? Well, today there are a lot of other areas similar, very deep, coral reefs. Can we explore coral reefs? Can we place sensors? Can we repair and maintain pipelines underwater? What we have done in robotics so far is amazing in terms of vehicles that can see, that can discover, find new boats, find sites, observe. But in terms of the interaction, the physical interaction, the ability to manipulate and repair, it is very, very difficult. And that's why recently we developed a new robot called Ocean One. Ocean One is a robot almost like a diver. So it has bimanual capabilities to manipulate, to interact with the world. It is the sort of robot that can eventually replace the diver, except that the diver doesn't have to dive. That is, the diver is sitting on the boat, and when this robot is going to touch the bottom of the ocean, the diver can feel in their hands what the robot is doing. This is coming from a concept that integrates communication together with robotics, together with haptics. So on the right, we have a haptic device, And on the left, we have a robot. And when the robot is here, we are going to communicate. This is attached on the boat to the human hand, and this is going to be doing the diving. We have a communication, very challenging communication, because underwater communication is not easy. We are using optical modem. There are a number of other platforms that are supporting those robots. The design, obviously, is not a simple thing. We started with the concept of head, arms, body. It grown into a full system that needed to be simulated, analyzed. Here is the early work on simulating this robot to interact, how we control it underwater. This is dynamic simulation with water conditions. And then we go to fabrication. It's very, very difficult to build robots with arms and fingers underwater. Many months and years of development. Finally, last summer, we were able to take this robot to the swimming pool at Stanford. This is only the body of the robot, that is the vehicle that is carrying the arms and the head, that was moving in August. And finally, in September at IROS in Hamburg, we were able to demonstrate this robot, in fact, interact with the robot directly from Hamburg through the haptic device to the Stanford, where the robot was operating in the pool. So a lot of happy students worked on this and succeeded, and now we are in a mission to take this robot actually to this boat in France called the Moon, and so our robot will be landing on the Moon. And the question is, this is only one example of many new areas. So can we help removing physically the mining person working in the dangerous conditions and somehow keep the miner skills through this interaction to use the tools and do the operation? So the miner will be interacting with the haptic device and the actual robot will be operating in the mine. For a geologist, is the same problem. For in astronomy, we have high altitude stations, difficult for a human. Can we operate them remotely? And this is something that is becoming very, very possible as we move beyond mobility. We have a lot of different robot systems that were built to observe in the air, under the water, underground, and we are now moving beyond mobility. So let me show you Hacia. Fantastic machine. It can run, it can jump, but for Hacia to be able to interact with the world so that it becomes useful, we need this robot to go beyond just moving. We need the robot to physically touch and interact with the environment. And to do a task like this, Hacia is capable of doing it. The challenge actually is not only the robot, it is the programming. Because this robot is coordinated, all the different motions are designed for this specific task. And the question is, how come a little child is able to do this task without having to think about the program? So what is amazing about human is that we develop those skills. And those skills are really unique. And if we are able to capture those skills, then the robot can perform different skills for different environment. So programming was okay for industrial robots. Today, as we move in the hostile environment, in the challenging environment, we cannot pre-program everything. There is also a very important point, which is that as much as we need robots, robots need us. We need to think about the synergy between robots and human. And this synergy brings amazing new potential for applications in very challenging environment. Here you can see on the left the hand of the human operating a robot to learn a task and to interact with an environment that the robot doesn't know. This ability to bring haptics, the convergence of haptics with communication and robotics, is allowing us to interact with robots deep in the sea, to move those robots, and to bring the human at not controlling every detail of the motion. The robot is autonomous. We are bringing autonomy as high as possible, but the human intuition, the human cognitive abilities are being used together with the robot skills. So we need to build those advanced skills. So to build advanced skills like human, we need to think about ways of learning from the human. So we are changing completely the way we operate the robot. We do not program the robot motion. We program the robot relationship to the world. We call it compliance and using contact. And using contact, we are able now to look how human perform the task and take those motions that the human is performing, not copy the motions, but extract the strategy that the human is using to perform those tasks. Now here, the robot that learned from the human to perform face-to-face operation between objects, despite changing the environment, changing the characteristic of the motion, or changing the grasp if we have error in the grasp. You can see now the robot is sensing the contact, having abilities to even adjust with respect to all the external disturbances. When we combine all of these together, the robot is able to make contact, achieve a relationship despite disturbances. The human is removing the robot, and the robot always finds its ways back alone without actually knowing exactly where things are. As we bring robots and the human together, we need to deal with safety. In industrial robotics, safety was addressed by putting the robot in a cage and telling a human be away from those robots. Now we are bringing the robot in our environment, and this robot needs to be designed not only to be safe, but to also be capable. And these two are always competing. So there is a big challenge in building mechanisms that are safe, and there is a lot of work all around the world. At Stanford, we are building human-like actuation with hybrid pneumatic and electrical actuation with sensing, skin type of sensing that is allowing us to feel and sense where the robot is operating. Another aspect of this is the fact that we need to understand human. If a robot is going to cooperate with a human, we need to understand the human model. So we took algorithms from robotics that model humanoid robots and apply them to modeling musculoskeletal systems. And now we can, in fact, observe human motion and study. This is an injured player from Stanford. We are looking at the motion, we are reconstructing the motion, and looking at therapy for helping exercising and removing dangerous motion that can be done by a human. We are looking at also improving performance. So here we are looking at how humans actually bring about high performance, and it turned out this is subject-specific. Every person has its own physiology, and there are specific acceleration lines that need to be followed to achieve the best performance. So we need to look at the human characteristics in terms of personalized measurement and characterization. We are even going further in our learning. We are looking at how humans represent tasks in the brain, and robotics is bringing a new capability to combining brain measurement with physiology measurement that we are able now to combine to get better understanding about the motor control in the brain. As we control robots, one of the biggest challenges is the fact that they are going to make multiple contact with the environment. And when they make contact, they are producing all kind of reaction forces. So those reaction forces requires us to be careful about the way we control the robot. We have to control the robot posture, we have to control the task, we have to control the contact, we have to avoid collision, self-collision. There are a lot of things, and we have to balance. Well, inspired by the way humans are controlled, we developed capabilities where the robot is human-guided. Now the robot is able to follow the guidance of the human, able to make contact with the environment without colliding with itself. It is avoiding collision. Here I'm asking the robot, do not touch my hands. And the robot will move its hands. It is perceiving the approach of the hands and creating a behavior that is avoided. This is not pre-recorded. This is behavior that are done in real time, which would allow us to take this robot to challenging environment where we can eventually replace human. This is a Fukushima environment where we would love to see humanoid robots operating instead of human. The problem is we still are operating robots with the assumption that the environment is flat. This is not going to work in an environment that is broken, and the only way we can do it is to do it like a human, where we are using actually the environment to support the motion. So multi-contact allow us to do that, and now we can take the robot and study the slippage of the arms at the contact, and despite changes in that environment, despite changes in the contact, we are able now to balance those forces and get the robot to be able to maintain those contacts. Now we can do climbing with a robot. In fact, I'm going to show you a robot climbing in environment that is so slippery that a human cannot do it. We are able to access all the data about the contact in real time and adjust the motion of the robot and balance the robot as it's climbing. As a robot is moving in the environment, sometimes we do not have the possibility to just make contact to support the robot biped motion. We will use tools like this. And instead of doing biped, we are going to be able to do triped, quadruped, we call it supraped. With supraped, we are going to increase the support area, and we are going to allow the robot now to plan, move, and make contact with the environment and advance. Well, this is not science fiction. This is being done today, and not only for one motion, but for a whole plan that is being modified in real time by integrating the feedback from sensors with a planner that is elastic, that is changing in real time, and allowing us to perform impossible operations that requires a lot of computations, but today with those methodologies of elastic planning, we are able to do it. So in the application of our underwater robot, where the initial project was aimed at dealing with coral reefs, fragile coral reefs, to replace a human where it becomes dangerous for a human to dive, to place sensors, to collect samples. What we have been doing was to build this robot in an environment where the robot is capable of making contact, manipulating objects, reaching to those objects, and this robot is part of a team. So when the robot is reaching for an object, there are other cameras here. The camera beneath is allowing us to see it and move. But when we have multiple of those robots, they can operate together, and they have to be robust. These are dynamic simulation. We are going to show that if we disturb the robot, there will be a red flash. We are going to push the robot from the back with this red flash, and you can see the robot is resisting those disturbances and is able to move and perform the task, continue the task. Now the other robot is going to reach, and the two robots are going to cooperate in a very challenging task to move this pipeline. Well, what is really interesting about all of this is we are not working for a specific robot, an underwater robot or underground robot. We are building capabilities that can be used by different applications, underground, in the ocean, in surgery, and in the field in general, because we are building those generic capabilities that are going to allow the robot to move and interact physically with its world. Thank you very much for your attention.